Okay, shall we?
Yeah.
Yeah. Hi everyone. Welcome to the afternoon sessions of GALOP'. So the first talk is the second keynote speaker for the workshop, and so Zhong Shao will talk to us about compositional development of certified system software.
Thank
Go
you.
ahead.
Thank you. It's an honor to be invited. This is my first time attend the GALOP' workshop. So I may not be speaking of orthodox game semantics terminologies, but you will excuse me. I'll give you a different perspective. So what's the problem that my group has been working on? We try to formally verify operating system kernels, or hypervisor or security monitors. It's kind of like a proof-carrying code, right? You have a system binary. You implement your operating system call specification on a piece of hardware, and you have a specification. You have a machine model. You try to show that the code indeed implements the spec. And what kind of a property you want to verify? You want to not only verify the functional correctness, but also security properties, resource usage properties, and sometimes even other liveness properties like deadlock freedom and so on. And you want to cut down the cost of verification, so instead of just a heroic effort. So the key point is what are these machine model might look like, what these software might look like. It's not the same as the traditional lambda calculus or the kind of thing, or not even a programming language that you often see. So I don't know whether you can actually see these little fonts, but this is like the CertiKOS OS kernel, concurrent OS kernel that we verified in 2016, where we have a multiple core, 8 core down below, and on each core you run these thread libraries. Then you have the main memory divided into many different regions used for different purposes. You have virtual memory management, and then you have these devices, and some of these devices are serial for keyboard, some are video drivers, and so on. So we literally need to model all these things based on however loose the specification is. And then all these blue box are the actual kernel modules, and the green box are drivers, and the gray box are data structures. So it's not the same kind of a lambda. I mean, you would think this is much more complex than lambda calculus. No, it's actually sometimes it's simpler than lambda calculus because mostly it's first order. Everything is compiled to the machine level representations. The closures are already represented as a code pointer plus some records and so on. And this is just the OS kernel itself. And in fact, when you deploy such OS, the machine does not just run this OS. They only run this OS inside some kind of a secure enclave or the trusted execution environment. Like this is one example deployment platform in our DARPA project where we have a Raspberry Pi 4, which is an ARM platform. You run some kind of a trusted firmware, which is verified by my colleagues at Columbia, and then we run in the trust zone, we run CertiKOS, and then in the normal world, we run actually vanilla Linux and others. So when you try to verify system property about such a system, you have mixed code from different places. And you only zoom into some particular code, you want to verify those properties, and you want to verify that if these enclave or whatever satisfy certain properties, the whole system will also satisfy these properties. So what's the connection between GALOP', right, between these two different words? One thing is for certain, right, we can't verify these code as a monolithic piece of code and we need a compositionality. We absolutely have to decompose these large pieces of system software, hardware into very small modules and verify them one at a time. But it's not the usual fork join concurrency or just the multi-thread, multi-core. Instead, you have all kinds of different things like interrupts, I/O device, and so on. So part of the job of formally verify OS is to try to figure out what are the compositional glues that glue these different pieces of code together. In other words, nobody knows how to do it. The OS developer probably did their best, but they know nothing about the game semantics. They have very primitive understanding of what can be made compositional. But we have these all kinds of powerful ideas from the GALOP community or game semantics community that we can apply. So that's a high-level question. And in fact, we don't know how to do these things. All these things are available. There's already code. We just have to read the code, understand how it works, and try to make it compositional. Because if we can, in fact, even this kernel is already organized with rather clean hierarchies with the modules built on top of each other. So it's already a lot of effort. If you don't look at any kernel we have today, it will have dependency edges going across from multiple modules with cycles, and it's virtually probably impossible to verify as well. So that's the problem. So just to roll back a little bit, like how do we started this project? We spent quite a few years trying to verify a very simple OS kernel for one properties, initially for partial correctness properties. Then we realized we needed to do security property. We developed another program logic. And then later on, we want to prove some other properties. We developed yet another program logic. And we soon find out that this is not practical because we can't go through the code again and again. So instead, we work on what we call deep spec project, right? So I don't want to go through these code again and again. I only want to verify them once, and once we are done, we will never look at it again, unless you modify the code, you want to redo some work. So the idea is that the formal verification of a kernel is always split into functional correctness verification. And the word deep is confusing. It's not clear what deep means, right? So we will come into that a little bit later. And of course, you can't do this for the kernel monolithically. So you divide them into many smaller C modules, and then you probably write a compiler. Use a compcert compiler, compile them to binaries, and then you try to link them together. And this is also too naive because we can't just divide the kernel code horizontally into different modules. In practice, the kernel is building the abstractions on its own. So the actual code you see here probably is dependent on the specification of the underlying layers. So that's why I wrote the spec itself as a more hierarchical spec, and you will verify it one at a time. So what's the deep spec? You are familiar with, anytime you do formal verification, you write the specifications, and you will ideally provide the rich specifications, and then you try to verify, one by one, and later on you find your spec is not quite right. You modify a little bit, and again, I don't really want to re-verify everything, right? I want to verify once. So ideally, I don't want to revisit, re-verify. So I want some notion of deep spec. What that means, I want the specification capture exact the behavior of the module. And what that capture everything about running a module. So here, I talk about the components as M, L1 as the underlay, the libraries you use, the specification for the library you call, and the L2 is like the export interface of M, which we call it overlay, the specification exposed by M. So I want the deep spec L2 behave exactly like M running on L1. And what do I mean by exactly same? There's some notion of a context. If you have a whole program semantics, P, then we want to, under any valid program context, these two behaviors are observationally equivalent with some relation R between the data structure representation. So if you have a deep spec, then hopefully when you verify the last modules, you verify once, and then you verify the next layer. You no longer need to look at the code anymore. So anytime you verify a piece of code, it's always local. It's always based on the underlay spec, you verify the overlay spec, and you never need to re-verify it again, unless you change the code, change the spec. So that's the methodology we used in the CertiKOS project. And we build all these things inside a cock-proof assistant. It's called the certified abstraction layer. The first kernel we verified in 2015, contains 37 abstraction layers. We basically carefully divided the 3,000 lines of C and assembly code into these 37 modules, where every module is absolutely easy to verify. But when you compose them together, it does the wonder, like create multiple threads, virtual memory management, and so on. And then 2 years later, we verified a concurrent version of this, added the concurrency support, and so on. So overall, what we did is inside the Coq, we use the CompCert as a compiler. It's called the CompCert X. We write each of these kernel modules in C Lite, and we verify the version of CompCert so that it can show that if you have a formally verified C Lite modules, when you compile to assembly, it will meet the same underlay and overlay specification. And then we have a layer library calculus allow you to do horizontal, vertical compositions. We actually also did a version of concurrency called the concurrent certified abstraction layer. And this picture is pretty messy, but all I needed to show you is you take the sequential one, you do the thread level reasoning, you do thread level composition, then you do the per call and the per call level verification. So we did this kind of in a brute force way and managed to get a concurrent kernel verified. But deep down in my heart, the theory is always look ugly, and we are try to look for things that's better than this. So other than so this tool, even though it's not the best tools, it has been successfully used by other projects. So like 2021, the Columbia team used to verify a KVM hypervisor and also ARM trusted firmware for CCR. So what kind of limitation we found? So this is where, so the first is we find that, this notion of a program context, which, in the morning, lots of people always talk about the observational equivalence, is with respect to program context. It's never clear what the program context of a module is, because if you remember the picture I show you, it will be the whole machine, it will have some hardware, components and software components. So ideally, I want to be able to build up the program context incrementally in a general language, and we should support open components, right? Like everybody mentioned in the morning, everything has to be open, but open in a way that we don't even know what eventually, probably it want to work on Mars, but at least on planet Earth, it should work, right, if it's usable. So some notion of an open context, a way to composing these open modules and to let you build a bigger system. So we have some recent work talk about how to extend this. The second one is related to the CompCert, where the previous compiler, version of a CompCert is not really compositional. So in the last few years, we have worked on an open version of it's CompCert all is open. So it's essentially a compositional CompCert for open components, like many of you mentioned in the mornings. And on Friday, my colleague Yiting will present a paper on how to extend the CompCert all with direct refinement, so that you can talk about the relationship between the source C program and the target assembly with a clear mapping from the source memory to the target memory. Surprisingly, that's not actually very obvious in CompCert because of the heavy memory injections used there. So we actually also try to work on extending CompCert to support multiple threaded stack, and how to generate a binary. So on the concurrency model, which is the focus of today's talk, so there's lots of restriction we did in our previous work. It's based on closed context. The threading model is rather restrictive. It does not support blocking concurrency very well. So things like lots of concurrency primitive. This is again kind of not being very, we don't see it considered much even in concurrent verification world, even in separation logic and so on. These are primitives that blocks, right? You sleep in a condition variable, sequential, queuing logs and so on. When you call it, you block yourself and go to sleep. And so that kind of code it's not clear how to verify them, and it does not, of course, support a weak consistency model. So this is one of the places we started to find the game semantic work really shine, and when we want to reason about these different things. So last year's Popper, we had a paper on the compositional theory of linearizability, which is what I want to talk about in the rest of today's talk. So the idea is linearizability is something invented by practitioners. Morris Hill, of course, he's a theoretician as well in distributed theory, but he's not from PL world. So linearizability is defined as a correctness criteria for shared memory concurrent objects. So what I want to show is it's something that done in the practicing side, we can actually turn it into a full-blown compositional. We can generalize it, and using idea from game semantics, we can turn it to become a general gluing mechanism for building general CCAR, concurrent certified abstraction layer, where to support all kinds of horizontal, vertical compositions. But first, let me review what linearizability is. So it's a concurrent object like Q. You have in-Q, DQ. If you do it a sequential way, you call DQ, it might return a value like empty Q, you return bottom. And if you have a concurrency, you will try to associate these calls with the thread ID. So in this talk, thread ID will be called alpha 0. So alpha 0 called DQ, return bottom. And you might have multiple threads, alpha 0, alpha 1, alpha 2, and they get interleaved, and you get this kind of interleavings. And when you have interleavings, alpha 0, because it's interleaved by others, it could return any kind of value because you don't know which one actually occurred, whether this alpha 0 is the linearization point occurred before any of these calls. So you could return possible different values. So the linearizability definition, classical linearizability, is basically saying you need to pay attention to what we call the happens before relations. That is, so if you have an interleaved execution, you look at every thread, the trace. Every thread, of course, is so-called sequentially consistent. You call followed by a return, followed by a call, followed by a return. And the happens before relation basically says, if a thread's call is behind another thread's return, that dependency has to be preserved. So linearizability says you can do the permutation of these events as long as you preserve the happens before relation, and if you can manage to permute it into a way so that it's fully atomic, like the Zhong Shao or the bottom, then this is what we call linearization. The top trace can be linearized to the bottom trace. And so the good concurrency development practice in the real world is you should always build a linearizable concurrent object because it simplifies the reasoning, because you can treat them as if, even though there's lots of interleavings, when you use it, it's as if it's fully atomic, which is why the linearizability is beneficial. But more importantly, linearizability has the following compositionality feature, which is called locality. That is, if an object is linearizable, you have 4 objects composed together horizontally. You actually have the if and only if property. That is, these 4 components composed together, then you can show each of them is linearizable. Or if 4 linearizable objects composed together horizontally, then the whole thing is still linearizable. This is very nice. Another property we also commonly see is called the contextual refinement property. That is, if we have a concurrent object linearized to an atomic object, then you can show that under any well-defined program context, the behavior of the concurrent object is contained inside the behavior of atomic object, which basically says you can use this concurrent object as if it's an atomic object. So both of these properties are nice. And of course, the linearizability is always something that we learn in the OS class, and you thought, wow, how could the people come up with such a deep concept, but it's not clear where it comes from, right? So it's a puzzle. So this is the work we did. We try to generalize the definition. We show that linearizability does not necessarily tie to atomicity. It works for any kind of specifications. And we provide a first model of linearizability that supports refinement, horizontal, vertical compositions. I will explain what a vertical composition means. And a general category theoretical methodology for deriving linearizability from a model of concurrent computation. So the recipe is, if I can play this trick on linearizability, then I ought to be able to do the same trick I'm presenting here to linearizability with the crash, linearizability potentially even with some notion of a weak memory and so on. So those are conjectures, work in progress. So we should be able to do all these things. So let me quickly go through what do we mean by compositionality exactly by some concrete examples. So when I say an implementation mu prime A implements a spec mu A, ideally we want to say that when I run some program on top of this library, they should also be contained inside the behavior P, program P running on top of an atomic version of this object. And then I can show that that piece of program running on top of this atomic object mu A also implements another object. That's ideally we want. But this thing immediately fails even for simple example like shared queue. So this is a piece of code where I have a sequential queue, right? And I have a lock. And the way people teach you how to do concurrencies, you always add the local quiet at the, then call the sequential lock, sequential queue in queue, then you release the lock, then you return. So that's basically a concurrent shared queue, how it's typically implemented. You want to use the idea from linearizability, it does not work. Why? Because remember that the contextual refinement only works for linearizable object. And this new Q prime, which is a sequential Q implementation, it's not even linearizable because it has arrays. It's a sequential Q. Clearly, it's not linearizable. So you cannot even use the locality. You cannot do that. And next, if you somehow somebody give you so there's a way to fix this problem, and one way to do it is you inlining the sequential queue into the body of the shared queue, and now lock is a linearizable object that could work. And in fact, the majority of the example, when people verify linearizable shared queue, they always inline it. They don't tell you why they inline it because it does not work if you otherwise. And of course, ideally, you prove a lock is a linearizable object because the lock is implemented using, ticket lock, use fetch and increment, counter, and some other primitive like yield. And now you want to vertically compose these because you have a lock. You have a lock here, and this lock is used by shared queue. You would think vertically compose them would work, but no, this does not work. Again, you have to do inlining. Okay. So this is what I mean by vertical composition. So when I talk about compositionality, I want a horizontal composition, which is a locality. I want the vertical composition so that I can lay one object on top of another. And I want to talk about the refinement between implementation and specification. So let me talk about what do I mean by sequentially consistent games or sequentially consistent computations. So the methodology is we first build a game model, a basic model of a sequentially consistent computation. Then we look into the reason why it's not a compositional by defining what the identity program look like, and then we compute a compositional model from the two, and then magically we see that all these properties we can model linearizability in a much general way. and all those property works. So when I talk about types, corresponds to game ABC. So each of these game ABC you could consider as an object with some method. So when you want to build a program components, they correspond to a strategy, like when I say L1, a module N built on top of an underlay L1, implements the overlay L2, it's a game from L1, arrow L2. So this A could be viewed as a effect handler, a module contains a set of methods. So program corresponds to strategy of type A, lolly B. Object specification is just something, a closed object does not take any parameters. And so this A could be a lock, B could be a shared queue, that's the idea. So how do we define sequentially consistent games? So with the sequential game is the same. You have a set of agent names. For each agent, within each agent, you define their usual sequential game strategies, one call followed by a return. Then the concurrent game is just a sequential. It's just sequentially consistent interleaving of all the plays by each agent. So this is a counter object, and the concurrent game is sequentially consistent interleaving of all these methods called by every agent. So immediately, you would start to ask, can we compose these two games? Yes, you could. So if you have two strategies, sigma and tau, you can, even in this concurrent game setting, you could show that it's associative. But it does not have an identity element. Because you do the parallel interleaving, it's not obvious what identity is. So you get kind of like a semi-category because you are associative, but you don't have identity element. You can prove something like refinement, monotonicity properties. You could actually show that if sigma is refined, strategy sigma is a subset of strategy sigma prime, you do vertical composition, and it's still refinement, behavior cantonment. So now let's look at identity strategies. So it turns out the linearizability is inherently tied to this notion of a copycat strategy. So in the sequential game, everybody understands. Sequential copycat is simply you make a call, then you call it self, right? It's like an eta redax, right? You call it self. And so this is what a copycat for each method inside a queue might look like. Now, if you try to potentially invoke multiple methods on this queue, you would the copycat will look like this. The opponent will call in queue, then you call the system call the in queue to the underlay, and so it will compose like this. When you talk about a concurrent copycat, it will be the parallel composition of these sequential copycat. So I just showed one instance. Now it's interesting, right? Because now you can do the concurrent interleaving of these two traces. And you can interleave the opponent events in any way you like, and you can interleave the events on the second line any way you like. That's exactly what the kind of a constraint it imposes on. But however you want to interleave it, you can interleave it any way you like, but these two events still have to be enclosed in the caller's events. And it turns out that's exactly the requirement of you have to maintain happens before order. So happens before order does not come from vacuum. It comes from what make a valid copycat strategy. So this is exactly how do we define the concurrent copycat. It's called C-copy, which is just a parallel composition of a sequential copycat. And you could show if you take a random concurrent strategy, you compose with this copycat, you would actually generate extra behaviors because this concurrent copycat interleaves things a little bit more. So the idea is that when you don't have a compositionality, when you don't have identity, one of the common techniques used in the category theory community is to use something called the Karoubi envelope. So it turns out the concurrent copycat I just talked about is idiopotent. So if you can prove a concurrent copycat compose 2 copies, it's equivalent to 1 copy. There's only that much interleaving you can create. So you do 2 versions. And so you can actually define what do we mean by a strategy is saturated by just adding a copycat, concurrent copycat on both ends. So if a strategy is saturated, then it's modular, it's more compositional. Because if you are only concatenate, if you only have a saturated strategy, they are always happy to add a C copy on both ends. Then when you want to compose them, those duplicate copycat will become 1. So that makes it more compositional, right? So this resulting category is actually a real category with identity. And now we basically have 2 models of computations. One is the semi-category game underscore conc, and another is the full category game conc. And one is good for composition, and one is good for specifications. And we can define a functor called k-conc, which takes any element from the semi-category to the full category by just adding copycat in the front. So that's what linearizability is. So we could define our new abstract version of linearizability, saying if a strategy nu A prime linearized to nu A from when the saturated strategy nu A prime linearized to a nu A, as long as it's contained in the closure or saturated closure of nu A. So that's what the abstract linearizability is. And a linearizable object can be defined as essentially, you can view that this nu A prime is the real behavior of what this object does. And this nu A is the specification. So do whatever, you can specify what your concurrent object is. It does not have to be atomic. It's just you think what the behavior should be. And this nu A prime is just adding the C copy on both ends. So even if this object is like a sequential queue, which has data races, that's okay. It's still linearized object as long as the actual behavior is you have a concurrent copycat wrapped around it. And of course, in the case of a single concurrent linearizable object, there's no parameter, so the C copy on the one end is a 1 unit. So the definition is just this. So you could prove that this is actually equivalent to the classical notion of linearizability. Actually, as early as 2004, Gika and Morosky has already introduced this notion of saturated, and shows that sigma is saturated if and only if these 3 rules are basically what we normally are allowed permutation in when we talk about the linearizable permutations. So officially, in our other than the notion of abstract linearizability, you can actually define the trace S is linearizable to T if there exists a sequence of SO opponent move and a sequence SP of proponent move such as. So essentially, this is just saying S linearized to T. SO is a set of pending invocation that not completed, and SP is a bunch of returns. These are the actual methods that are actually already completed, and you use this rewrite system to allow the permutations. So that's the linearizability definition. And you can show that you can prove that the abstract linearizability and this this rewrite-based linearizability are exactly equivalent. So that basically means a copycat, concurrent copycat, and these set of rewrites are equivalent. All right, so yes. So let's talk a little bit about actual properties. So you could actually prove. So what is the contextual refinement? Remember, I don't want to. I want to define a refinement without talking much about the whole program. But in the concurrent object setting, I basically want to prove something like this, right? I want to prove if I'm object A, and I prove that it's linearizable, which is here, then I want to show that any of the saturated strategy, any of my client object, whether it's any sigma, I have this property, meaning that running sigma on top of my concurrent implementations is contained in the behavior of running this sigma on top of my, linearized spec mu A. So this turns out to be, this is very general because I can do NAB, right? And it turns out to be very easy to prove because I can use the monotonicity property of the refinement because this is a refinement of this, and adding composing a strategy on top, it's still the refinement. And then because sigma itself is saturated, so C copy simply gets absorbed. So I immediately get this notion of contextual refinement. The backwards is just a matter of choosing sigma to be C copy A. So you would be able to get that too. And then you also can prove horizontal compositions. So you define, so the horizontal composition of two concurrent objects is defined as some kind of a tensor product of two strategies. So sigma tensor tau is a sequentially consistent interleaving of sigma and tau. And actually, if you added this tensor product, you get a symmetric monoid category for game count. And you can actually show that this tensor is a functorial, and you could prove a concurrent copycat equivalence of a C copy A, tensor C copy B is C copy over the A tensor B, all the right properties. And you can use the monotonicity property to prove this, and autoisomorphism to prove the reverse direction. But basically what this allows you to do is to prove the locality or horizontal composition of the Y two linearizable object. If you have two linearizable objects, you tensor them together, you get another linearizable object, and this is if and only if. So you can, the proof is actually just the basic composition of these different properties. So in contrast, if you go to the classical paper in 1990 to look at how they prove locality, it's actually have to prove by contradiction. And so it's very subtle, very complex, where in this case, it's a much general result because it's no longer tied to atomic spec, and the proof is much simpler. So once you have that, now I can actually prove all those examples I mentioned at the beginning, like shared Q. It's not a problem with I can use a new sequential Q because it's also a linearizable object. I can actually prove each of these separately and do the vertical compositions. Sorry. Right, so I can prove the top one, and then I compose with this log to do the vertical composition, and that would allow me to prove the shared Q together. I think I missed one slide here somewhere. No, it's correct because this is M shared Q. This is log is implemented by M log, so then I can put them together. So we actually defined the program logic to verify this. So this is how do we put these two pieces together. And the sequential queue is proved, its implementation is just the identity C copy. And so I can do the locality, I can do the vertical composition. I can show this example completely using our formalism. So in the actual pop-up paper last year, we have all these other results, which you guys are welcome to check out. In particular, it shows we can apply this idea to other kind of a linearizable atomic spec, not just the sequentially atomic, but also something called the interval atomic, which is much more general than the traditional atomic spec. So I want to conclude that by just mentioning that there's something that come up in our world that is, when you verify system softwares, we don't have the notion of a program context. We kind of want this kind of a fully abstract deep spec, and there's a lot of usage scenarios there. The concurrency model I showed you so far is very simple. It's a flat, multiple agents. There's no dynamic thread creation. It's a model multi-core. But in practice, if you remember the picture I showed, even for the CertiKOS kernel, there's a multiple core, multiple threads. There's a timer interrupt. There's a device, and so on. So, and that's a usage scenario that kind of desperately need the help of a compositionality, because there's no way I can verify any of those if I don't know how different pieces together. And that really requires people like you who have who got your PhD with the compositionality in the blood, and and so many of these things would benefit from your expertise. It's just the emphasis is slightly different. The compositional abstract machine may not look like things you see before, but sometimes it's simpler because it's first order most of the time. It has a finite resource, but what's most interesting is you don't have to work from scratch. In the worst case, you just need to look what the current practitioner is doing, right? Because somehow these code has already been written. They are reasonably compositional because they are being maintained by kernel hackers, and it runs on today's machines. And so supposedly it's reasonably good. So you can actually reverse engineer what the principles they use. And of course, they are never always, so this one works, but okay. Yeah, so they are never exactly the same, which is why the research is necessary. Yeah, I will stop here.
Okay, yeah, we have a couple of minutes for questions. Yeah, Ugo.
I'm wondering how much of what you said also work for quantitative properties like, for example, running times, space consumption, these kind of things. Also, like more intentional properties can be dealt with, or?
Right. So now most existing software are not written with the resource usage in mind. There are some things that space usage is something it's often overlooked. So I'm not even talking about how much memory you would use, whether this module could potentially use infinite memory or something. So when you guys work on memory allocator or thread creation, creating new threads and so on, it turns out the majority of the kernel memory allocator are not secure or not safe, because the kernel always have a memory allocator shared by different services. And so you create a IPC channel, you need some memory. You create a new thread, you need some kernel memory. So you could intentionally write a piece of code that make abusive use of one library and then run out of the memory for the others. So in our, for example, verified kernel, we have to divide our memory allocator into different kinds. One for this type of object, one for another type of object, so that we can show they are not going to. So that kind of coarse-grained things are even overlooked by most of the kernels, but when you verify it, you have to verify the property, you often look into it. For time, it's even worse. Nobody cares about the time, except in the real-time community, people do care. But it's always hard because the cache side channel is, most of today's machines are not very accurate in giving you the cost models. So the most common way is to set a timer and counting on you will finish your computation within a time bound. And then when the timer triggers, then even if you still try to run, we will just preempt you. So when you write your code, you would basically always say, let me calculate something in case I get preempted. And then
you instrument your code with the count.
Yes. So there's a fallback. And I think that's pretty popular. That's how to get something without doing the kind of hard work you guys do, cost model analysis and so on. Right?
Any other questions? Yeah.
A very naive question, because I know very little about operating systems, but I guess my question is, how applicable is this to a notion where you have kind of microkernels and dynamically loadable modules? Is it a framework in which kind of this composition can be done dynamically in some way, or is it about statically verifying a kind of complete composition of modules into an operating system?
I don't think it's that related. So all these so-called dynamically allocated kernel or dynamically allocated thread, context, and so on, in the kernel, it's still kind of semi-statically allocated because you can't arbitrarily increase your kernel resource. You always have a bound about how much memory you have. So you often pre-allocate a pool of space, and then you try to use up some of them. And now, yes, you could say, when you run out, you could ask for more, but then the question is, how many times you can ask for more? So it's still, the model is, it's never like the one you guys wrote on paper, which you allow you to infinitely allocate as many memory, as many space you want, because that's not what's going on, right? So it's always have a bound. Once you have a bound, it's kind of the distinction between dynamic and static is not that different.
Okay, maybe we should move on. But thank you very much again, Zhong.
The next speaker, just so you know.
You're the one after. Okay, thank you. Hello. What's your name, Jack?
Jack. Very strange name, I know. We get it mixed up a lot.
Do you have a belt?
All right, cool. I just bricked my system this morning, so thank God I was carrying an Arch Restore USB. It's fate. Okay. View as. Is it going to start?
Yeah, I don't know. Yeah, go ahead.